Alright, so this video is on the second derivative test for Math 1560, Calculus 1 at U of L for fall 2017. So this comes from section 3.4 on concavity, and this is our second attempt at this video. We had audio problems the first time around, so we're going to try and correct that this time. Okay. Now, we already know the first derivative test, and in most cases, the first derivative test is still the best way to go, right? If you have the sign diagram for f prime, right, once you know the sign of f prime on either side of your critical point, you know exactly what's going on at that critical point, right? Because at your critical number, you've got your critical number here, and we know that there's really only four possibilities. You could be plus plus, you could be minus minus, you could be plus minus, or you could be minus plus, right? And so the first two, when it's the same sign on either side, well, depending on whether that critical point is a place where the derivative is zero or a place where the derivative is undefined, you might be looking at either a horizontal tangent or a vertical tangent. The other two, if it goes from positive to negative, we know that's a max. If it goes from negative to positive, we know that that's a min, right? So the first derivative test is pretty foolproof. It only has one limitation, which is sometimes getting those signs is a little bit difficult, right? And so here's a couple of basic examples where it might be kind of hard to do, right? So let's say I've found the derivative in this first one. I got a degree 4 function. I calculate the derivative. I get a cubic polynomial. And I've got one critical point, and maybe I got that critical point just by guessing, right? Using the rational roots theorem. So you might remember the rational roots theorem says you look at the numbers that divide evenly into the constant term, you look at the numbers that divide evenly into the leading term, and the possible rational roots are going to be, in this case, the divisors of 9, possibly divided by a divisor of 4, right? So you would have, you'd have plus or minus 1, plus or minus 3, plus or minus 9, and then you would have plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 9 over 2, and then plus or minus 1 over 4. Anyway, you get the idea, but there's lots of checking. So maybe we got lucky, we found this one value, right? But we haven't factored f prime. So if we wanted to continue on in factor, we would have to do long division to factor out the term coming from the c equals minus 3 over 4, right? We know that this one would come from a 4x plus 3 factor. But we would have to do long division to get the remaining quadratic, and then we'd have to factor the quadratic, and then finally we could do the sign diagram. So there'd be a fair amount of work involved getting that sign diagram, right? The other one, well, the critical number happens at a point that isn't kind of all that nice to work with, arctan of 3 over 4. You could use test values to work out a sign diagram, but again, it might be easier to look at the second derivative test, if you know what that is. So let's explain how the second derivative test works. So the second derivative test allows you to analyze that critical point by considering the concavity of your function at that critical point, right? So remember that if the first derivative is, or sorry, if the second derivative is positive, well, that means you're concave up, right? And we're in a situation where the first derivative is 0, right? So we're at our critical point, right? We've got our critical point. We know we've got a horizontal tangent at that critical point, right? And concave up, remember, means that the graph is curving up away from the tangent, and that the tangent lies, so the graph lies above the tangent. So we know that concave up means that we have to look like that, and so we can see that indeed we have a minimum, right? Similarly, if you've got a point where the derivative is 0, so you know you've got a horizontal tangent at that critical number, but you're concave down, right? The second derivative is negative, so you're concave down. You know that means that the graph lies below the tangent, and that must mean that you look like that. So you've got a maximum, right? The only problem is that, well, the second derivative test doesn't tell you anything if the second derivative is 0. It also is completely useless if the first derivative doesn't exist, right? Because we know there are some critical numbers that we obtain by finding places where the derivative is undefined. The second derivative test doesn't apply in those cases. It doesn't apply if the second derivative is 0. It only applies in this setting where the first derivative is 0 and we can determine that the second derivative is either positive or negative, right? In these two basic examples, we can see that, for y equals x cubed, right, the graph looks like this, right? But when we calculate f of f prime, right, f prime is 3x squared, so f prime of 0 is 0. We have a critical number at 0. But f double prime is 6x, also equals 0 at 0. Whereas if we were looking at the graph y equals x to the 4, right, well then that graph looks very different at 0, right? We actually do have a minimum there. But this time, we calculate g prime, 4x cubed, g double prime, 12x squared, right? And so the second derivative is 0, so we can't use the second derivative test. Fortunately, in these cases, it would still be easy to apply the first derivative test, and so we could just do that. So let's finish this off by just coming back to those two examples that we started out with. Right. So the first one, we've got this this degree 4 polynomial, and we want to classify this critical point. So we need our derivatives, so we calculate f prime, 4x cubed plus 3x squared minus 12x minus 9. And I'll leave you to check that f prime at minus 3 over 4 is indeed 0. F double prime, we get 12x squared plus 6x minus 12. Okay, so 6 times 2x squared plus plus x minus 2. Okay, and so if we wanted to calculate f double prime at minus 3 over 4, it's going to be 6 times 2 times, if I square minus 3 over 4, I get 9 over 16, minus 3 over 4, minus 2. Well, this is going to come out to be negative, right? Because minus this number here is going to be just a little bit bigger than 1. It's 9 over 8. It's a little bit bigger than 1. But the other two terms are negative. So this is negative, which means that we're concave down, which means that we have a local maximum, right? Similarly here, we calculate g prime. We get minus 4 sine x plus 3 cos x, and you can check that g prime is going to be 0 at this critical number. G double prime, we get minus 4 cos x minus 3 sine x. And okay, now we have to do a little bit of work, right? Because let's draw a little triangle. C is one of our angles. Tan is opposite over adjacent. The remaining side is 5. So cos at so g double prime at c is going to be, so cos of c is going to be 4 over 5. Sine of c is going to be 3 over 5. But we can see that definitely that's negative, right? And so again, because the second derivative is negative, we know that we're dealing with a local maximum. Okay.